MacMaths, let's do some maths today. Okay, it's this series of connected particles, and this is part D, and we're looking at blocks connected by a rigid rod. Same as the first one really, but not a string, a rigid rod. And that happens in tow bars in cars and trailers. Okay, let's do that one. Alright. So let's go back to part A, and remember we started off, didn't we? Started our journey with two blocks, 4 and 2 kilograms, and they were attached by a string. So why are we going to replace that with a rod? Because if we replace it with a rod, it's all the same maths, as we're going to see with cars and caravans. It's all the same maths, but it allows us to look at one different situation that would happen in reality, and that is that if it was moving and we put the brakes on this leading object, if we put the brakes on where it was pulling before, now it's slowing down, and this one here is pushing up against it, and it changes what we call tension when you're pulling to when you're pushing to thrust. So you can't have thrust in a string because it would just all concertina up, wouldn't it, and squash up. But pulling something creates a tension, pushing in it, mathematicians call that thrust. So every time a car brakes with a trailer on the back, it compresses the tow bar rather than creates tension in it and stretching it, or trying to stretch it. It doesn't really stretch and squash, does it? Okay, so that's what we're going to look at. For an example then, so let's have a look at a car and a trailer. So I'm going to set up a trailer, so I've done a little example for you. So there's my, if you like, a caravan, and a tow bar, and a car, or one of those sort of 4x4s, there it is. And we've got a tow bar between them. I've lengthened it so I can get my arrows in. And I'm going to put on an engine force. So the engine creates a force. Now in my example, my engine's going to create a force of 1,800 newtons. That could be about right for an engine of a car. The car, I'm going to say, weighs 1,000 kilograms. Again, if it's a big car, a hefty car, then that is feasible. Caravans and trailers don't contain engines, so they tend to be a lot lighter, and I'm going with 600 kilograms for this. Okay, so you may get a question talking about a car and its trailer, or a car and a caravan, the engine force that's applied, and so on. And the questions you're going to get asked is about the tension in the tow bar and the acceleration. Now, the one thing that we can't get away with here, I know we've been saying like air resistance is negligible and friction, forget that, and so on, but actually a car and a caravan create so many resistances to motion, even on the flat, even before we start going up a slope, that we just can't ignore resistance to motion. So air resistance is quite significant on a big bulky thing, not like a little stone that we throw, and also sort of friction in the wheels and so on. So when we're doing this, we can't ignore them. So if you get a caravan and trailer one, you'll always get resistance to motion for the car and the caravan, and you'll have to either work it out or they will tell you what they are. So I'm going to give you some, and I'm going to say that the resistant for motion, two resistant forces, 250 newtons for the car because it's bigger and clumsier, and 150 newtons for the trailer. So in a question that you get on trailers and cars pulling trailers, you'll always get resistant forces. They can't ignore those, otherwise it wouldn't be a great model. It would be too unrealistic. Okay, so let's do this. So part A is the same as our two blocks effectively, and it's just a slightly more complicated because there's just another couple of forces to take into account, these two forces here. So if we work out the acceleration first, so A, the acceleration, and then we'll work out the tension in the tow bar. So remember what we said, that now in these situations, if you consider it as a whole unit, okay, so this is, if we say F is equal to MA, the force pulling it is 1,800 newtons, okay, but now it's got some resistant forces, hasn't it? It's got a 250 and 150. so that makes 400 newtons. So the net force pulling the whole thing is 1800 minus the ones that are holding it back. That's our force, our net force. And remember what we're doing, we're considering it as a whole unit. We're going to separate it in a minute, but where we can, we consider it as a whole unit. And it's the mass, well, the mass of the whole unit, you can see, is 1600 kilograms and acceleration. So there we go. And we've got 1400 is equal to 1600 A. So divide both sides by 1600. So 1400 divided by 16. And that tells us that the acceleration is 0.875 meters per second squared. So we've got our acceleration. Okay. Now then, tension in the tow bar. So tension acts away, doesn't it? So it's acting away from the car. So it's dragging the car back. But it's the actual tension that is pulling the caravan. So we consider these separate. I can either use this one or that one, but remember I've got to include these here. I've got with the whole thing now, which helps massively. I've got that, haven't I? The acceleration. So considering them separately, I'm just going to go with the caravan. So this is my caravan, my little diagram. There's my caravan. And it's got T pulling it that way. And it's got resistant force of 150 newtons in air resistance and friction that way. But it is accelerating. It's at 600 kilograms and it is accelerating, same as the car because it's attached at that. So applying F equals ma to our trailer, the net force pulling it is the tension. It's tension minus the resistant forces. So that's the pulling force, and that's more than this, isn't it? So that take away that is the overall force that's pulling our trailer. So we've got 600 times the acceleration, which is 0.85. So the tension is 600 times 0.85 plus 150. So 600 times 0.875, I'm putting 85 in there, but I didn't mean to do that, plus 150, and that gives me 675 newtons, and that's the tension. Okay, so same as lesson part A, the only thing is I had these, didn't I? These resistance to motion forces. Okay, now there's a part B to this, and the part B is that you're going to get asked about what happens when this vehicle starts to brake. Now I've done a sort of a mock-up of that. So first of all, what happens when it brakes? When it brakes, instead of pulling, that that brakes and that is pushing against it. And what we do then is when it's braking, it creates what we call not a tension but a thrust. Okay, so on this particular question, let's get rid of those now. That's the first part. Okay, on this particular question, I'm going to say that the vehicle has reached a speed. So after reaching a velocity of 15 meters per second, okay, and what have I said? I've said, I'm just reading my notes, I posed a question and it decelerates for 100 meters to stop. So decelerates for 100 meters to stop at lights. Okay, and you've got to find the thrust. Find the thrust in the tow bar. That's the force that creates in the tow bar. Okay, so let's do that. Well, first of all, we need to know the deceleration because it's going to start to, if it hits the brakes, it starts to slow down. So first of all, this here, this 1800 newtons has gone. Okay, so it's not pulling it anymore. Okay, so that's taking the foot off the accelerator that's causing the engine to work, and he's hit the brakes. So there's a braking force now. Okay, And that braking force, we can work that out, but what we're going to do is we're going to use equations of motion now to find the deceleration. So if we use v squared equals u squared plus 2as, let's just shift this over so I've got enough room. So v squared equals u squared plus 2as. So we want it when it stops, so it's going to travel 100 metres, and v is going to be 0, isn't it, when it's stopped? And the initial velocity, of course, is 15 metres per second to the minus 1. So velocity is 0 is equal to 15 squared plus 2 times the acceleration times s, which is 100. So we've got 0 is equal to 225 plus 200a. Take that over to the other side, and we get 200a is equal to minus 225, and a is equal to minus 1.125. And we expected it to be negative, didn't we? Because it's slowing down. So now the acceleration is minus 1.125 meters per second to the minus 2. Okay. So that's that first part. So we've got that now. Now we can start working out the forces. Now all I want is the thrust. So what's happened is that when that hits the brake, then the thrust means that the force, and I'm going to call that TH now instead of T, pushes against the van, okay, and it pushes against the caravan. So to work that out, we're just going to consider them separately again. We've got a new acceleration, and I'm just going to look at the caravan. Okay, there's the caravan. Okay, so first of all, we've got 150 newtons acting that way. We've got the thrust, which is acting also that way. Pulling it, we've got no force. Okay, and if we apply F equals ma, there's no force pulling it now, because the two forces are the thrust and the 150. The pulling has stopped now because this is braking. So there's nothing pulling it minus the two forces opposite against that, 150 plus the thrust force. Okay, because remember, these are, you've got to get direction in, and that's a minus 150 if that way is positive. So this becomes a minus force also, and that is equal to the mass, which is 600, times the acceleration, which is minus 1.125. Okay, so there's the maths. Being careful with thinking about direction and forces. This actually, if I just go minus 150 minus all that minus the thrust is equal to, so 600 times 1.125 is equal to minus 675. Okay, so that times minus that is the minus 675. Now if I take the thrust over there, because I want the positive, and then that over there, that's add to that side, I've got 165,675 minus 150, and that gives me 525. So the thrust is actually 525 newtons, and there's 525 newtons pushing that way. Okay, so there's the thrust, that's the opposite of the tension, that's the push in there, and it's pushing 525 newtons up the backside of the truck also. Okay, so that's what happens when things decelerate. We create this thrust, and now I've got a question for you to have a go at. So I want you to put it on pause. Let's get my question here, and it's the same sort of question as the one I've just done. A car of mass 800 kilograms pulls a light trailer of 100 kilograms, joined by a towbar. Resistant forces for the car and the trailer. So I've given you two resistant forces for those, put them on, and the driving force, same as the question I did. This time I've given you the thrust in the towbar, so I've given you that, and you've got to find the braking force of the car. So the force that the brakes create to slow the car down and the deceleration of the car. Okay, so put it on pause and have a go at that question. Okay, right, I hope you did something like this. Well, I'm hoping actually that you drew a diagram to start off with. So let's have our trailer, pretty good trailer actually that, and a car. Oh, less good. There's my trailer and car, joined by a tow bar. This is 800 kilograms. This is 100 kilograms. We've got some resistant forces, we're going to have those, so 150 for the car, 40 for the trailer, and a driving force of 120 newtons. So part A, the acceleration. So the acceleration, we're going to go F equals ma. The driving force is 1,200 newtons minus the resistant forces, so everything working against that is going to be 190 newtons. That's those two adding together. And you can see what I'm doing. I'm doing it as the whole thing is equal to the mass, which is 900 times the acceleration. So this is, that take away that is 1010, is that right? Yeah, it is equal to 900 A, and then if we divide 1010 divided by 900, I get an acceleration of 1.12 recurring meters per second. Okay. Now we need the tension. Tension acts away. Let's put it in and away from that. We can consider these separately. So just looking at the trailer separately for part B, the tension in the tow bar, then we've got, there's our trailer, 100. We've got 40 newtons acting that way, and we've got the tension that's actually pulling it. But now we know, crucially, that it's got an acceleration of 1.12. So we can apply F equals ma. The net force is going that way, so it's that take away that. So T minus 40 is equal to the mass, 100, times the acceleration, 1.12. So that's 112. And if we add those two together, we get 152 newtons. Okay, so that's the first part done. Now, the driver spots some traffic lights and it causes a thrust of 40 newtons in the tow bar as he's braking. So the braking force of the car, the deceleration of the car and the trailer. Okay. Let's do that. Okay. Okay, so we've got now, I'm just thinking about how to do this now. So what I'm going to do is I'm going to separate out the two of them. So the driver spots some traffic lights and it brakes. So if I just look at the trailer here, this tension that was pulling that way is now pushing, isn't it? And that is a 40 Newton force there, it's pushing against it. And of course it's got 40 newtons they're acting that way as well. That's the resistance to motion, and they stay the same here. We don't know the acceleration, we're going to find it in a second, and we're going to do it the other way around actually, aren't we, because this is the easiest way of doing it. And we've got that as 100, that's the the mass of the tow bar. We could have done it the other way around and found that the force first of the brakes, but it would have meant a more complicated equation with the first one and doing a simultaneous equation. So it's easier to do it this way around, actually, just thinking about it. So we can just apply F equals ma. The pulling force in that direction is 0. So the net force is 0 minus those forces acting that way, which is 80 newtons. That's the driving force making it go that way, which is 0. In other words, minus 80 is actually slowing it down, is equal to the mass times the acceleration. And so you can see here that actually we just got minus 80 divided by 100 is equal to the acceleration. So the acceleration is minus 0.8 meters per second squared. So it's decelerating by 0.8 meters per second squared. And now when we look at the engine, there's the engine, we've got the thrust now is acting against the, is the other way around. So we've got 40 newtons now, the thrust that we're given is acting that way, and the braking force of the engine now is acting to slow it down. Okay, so that's the braking force of the engine, and that braking force is creating a deceleration of minus 0.8. So this is 800 thingy, and there's resistant forces still, so there's 150 newtons. Yeah, going that way. So there we go. So let's apply F equals ma to that. So what is acting that way, driving it forward? We've got 40. And 40 is being combated against 40 is these two, which is, we're going that way is positive. So that is a positive force pushing it that way. These, which we know are going to add up to more than 40, which is why it's making it slow down, is 150, okay, plus the force, which is now the braking force of the brakes in the engine, if that even makes sense what I've just said. We've got is equal to the mass, which is 800, and we know the acceleration is minus 0.8. Okay, so that times that is going to be minus 640, isn't it? And we've got 40 minus 150 minus the F. Okay, so we take the F over to that side and take the plus 640 over to this side. We get 640 plus the 40 is 680 minus the 150, and that is going to be 530 newtons. And that is the braking force. It's a negative force because it's working in that direction, okay, to overcome it. So we have to be very careful about direction here. All right, and you can see that is positive, so put that in as positive and these ones in the formula as negative. Okay, and it comes out as 530 newtons. All right. Okay. So 40 take away 150 and take away a 530 Newton force would cause it to decelerate by minus 0.8. Thanks guys, and that's your cars and your trailers all sorted.